Hi, my name is Bert Baumgartner. I am a professor here at the University of Idaho in philosophy, and I also have a big interest in artificial intelligence. What I'm going to do here is give you an introduction to the idea of MARC. This is an abbreviation for the Metaphor Abstraction Reasoning Corpus. It's inspired by a kind of benchmark that has been developed by Francois Chollet that I'm going to give you an introduction to here in a second, known as ARC, the Abstraction and Reasoning Corpus. And the main motivation behind this kind of benchmark, unlike other kinds of benchmarks, is for the tasks to be really easy for humans, but to still be very difficult for AI to solve. The primary reason for this is that there's a feature of human intelligence that allows us to be able to deal with novelty in new situations. And the kind of novelty that a lot of AI agents that are being currently developed don't seem to have is that kind of novelty, even in really, really simple cases. So I'm going to show you what ARC looks like. This is the benchmark that I'm inspired by, and then I'm going to tell you a little bit about MARC as well. If you prefer to read this, I have actually a post that I've done on my Substack that you can go check out. This is, I'm going to share my screen here. If you go to robotbert .substack.com, you'll see one of my earliest articles is this one, Easy for Humans, Hard for AI, the Metaphor Abstraction and Reasoning Corpus. So most of the things I'm going to talk about here is actually written up with some examples there, and I'll expand a little bit on that in this video. Okay, so let's start with ARC. What is ARC? If you go to the arcprize.org website, you'll see some examples of these kinds of tasks. So in an ARC task, you're given some input examples and, these input-output pair examples. So if you look in this first example, there's an input where you have these sort of 3 pixels these 3 pixel objects. Then you have an output where you've given or you've seen, right, that it's been filled in with this darker blue image to finish up these sort of incomplete squares that are then finished up. In the second example, you get another one like this. You get these like little L-shape figures, and then you need to fill them in with these darker blue. So you're shown these examples, and then now you're given the test. So you have this input here, and you need to figure out what the output should look like. And so what you can do is change the size of this grid world. It can be anywhere from 1 by 1, so 1 pixel grid, or up to 30 by 30, and anything in between, and they don't have to be a square. So I could, if I wanted to, create a much bigger output, but here it looks like in all the examples, the input and output have always been the same grid size. So I'm going to keep those the same. And then I can draw what I think is supposed to be the output that is intended by this test. And to make it a little bit easier, I can just copy from the input by hitting this button, and then I can pick this blue square, and I'm going to fill this in because I think this is my guess of how to solve this problem. And then I can submit the solution to see if it's correct, and sure enough, that one was correct. It's pretty easy. One of the things that's a bit surprising is that a lot of AI systems find this quite difficult to do. And one of the things you can do is sort of read the history of how the models have gotten increasingly better over the last 5 years, but still, even the best ones are struggling substantially. And what I mean by the ones that I'm sort of talking about here, it's the ones that are like accessible to us. There are a handful of examples now that have been developed in these sort of frontier models that seem like they're scoring a lot better, but they're proprietary and we're not quite sure exactly why. Okay, so that's the idea of ARC. There are some examples that you can see on the ARC Prize webpage. So again, you're given these sort of like input examples that tries to sort of demonstrate to you what the task is, and then you're given a test input that you have to create into an output. My idea is to extend this kind of benchmark to examples that are of interest to my areas of research, and I think key things that I'm trying to understand in the world of AI. And there's two parts for this, and the main one is this idea of MARC, or the metaphorical reasoning. So let me show you an example that I have to illustrate. So here are three task demonstrations. This is the input on the left, and then the output sort of on the right. And then you have three of these examples. And what's different from ARC is that I'm also going to give you a kind of clue. So that clue is some description or some sentence or some kind of statement, and it's supposed to help you sort of see more quickly what the potential solution would be. So the clue in this one is bigger frogs get eaten first. So if you look at the examples that I have, you might think, okay, what gets to count as the frog? Especially knowing that the frogs are supposed to get eaten. So in the input, I might look for certain things, certain candidates that I would identify as frogs. And in the output, I need to see, okay, have they disappeared? And if those things disappeared, those are the good candidates for frogs. It's metaphorical in that the shapes themselves might not actually represent anything that like visually corresponds to frogs, or maybe they do, right? But the point in a metaphor is that that needn't be exact. The other thing about the metaphor here, and this is what I think will be of interest, especially to a lot of humanities scholars, is there's a bit of a story that you can think of, or some kind of narrative that will help you sort of think about like in between steps that took us from the input to the output. So if I said bigger frogs get eaten first, you might look and see, okay, this image right here and this little green spot over here, since they've disappeared in the right side, they're going to be the candidates for being frogs. But the in-between steps require there to be kind of predator that needs to have gone somewhere and ended up somewhere, but I don't see the in-between steps. So here, if there are two frogs, this big one here and this little one here, and if the red pixel seems like it's a good candidate for being the predator, then it should end up wherever the smallest candidate frog is, which is the story that I've told here with this output example that you're given. In the second test pair, you might again look, okay, which things have disappeared between the input and the output? That might give you some clues about what the candidate frogs are. And you'll notice, again, there are some like different kinds of shapes. You're like, none of the shapes maybe don't seem to matter so much. But here again, we see that there's at least one green pixel that corresponds to the relevant shapes that we think might count as a frog for this metaphor. And if I look at the size of each of those, the top left one, this green square, looks like it's the smallest one of what the candidate frogs are. And the red pixel then ends up being at that last position. And here it looks like the red pixel, which is thought to be the predator, is in the position that is furthest away of that frog. Okay, I'm given one more example here at the bottom. And the thing that's a bit curious here is to note that there isn't any kind of change between the input and the output. So that causes me to think, okay, maybe there are no frogs, right? The bigger frogs get eaten first. If there's no frogs to get eaten. And so that would explain why the predator hasn't moved in any positions. And it also tells me something important about the shapes not mattering nearly as much for what get the count as the candidate frogs, compared to there being at least one green pixel when I compare that to the earlier examples. So now I move over to this test case. I'm given an input and I'm given a bunch of shapes, and I have to think about which ones might get to count as the candidate frogs. I've kind of learned by looking at these examples that as long as there's at least one green pixel, then whatever the cohesive object is would get to count as a frog. And so in this image, it looks like there are three candidates. There's this L shape of pixels. There's this sort of star shape that I've seen before that gets to count as a frog, so long as there's at least one green pixel. And then there's also just one green pixel over here to my right. So there's three frogs that could get eaten. And the metaphor again here is the bigger frogs get eaten first. So it's a metaphor because I'm taking that sort of sentence and trying to use that to understand what's going on here in these pixel worlds. And in this case, I can, at least the way I'm sort of reasoning about this, is that this red pixel will end up in this right one over here. It will have eaten that last, and in between it will have eaten these other two. So I can copy from the input the grid size, and this is also important. The grid is different here in terms of it's higher than it is wider. So if I copy from the input, it will just make sure that the grid size is exactly the same. And what I'm now going to do is sort of recolor these pixels to match what I think the solution is supposed to be. And take this green one out and put the red one there. And then the red one will have moved over into that position. And so now when I submit this, I see down here that I got the correct solution. So what's interesting about this extension of the ARC idea is that there's supposed to be some kind of phrase that makes the solution seem a lot more obvious. Of course, there's always going to be an infinite number of different kinds of possibilities. What's interesting about ARC and also this extension that I'm calling MARC is how much coordination there is and how much convergence there is in humans doing these kinds of puzzles. So that suggests that we are using something really similar in terms of our reasoning to help solve these kinds of puzzles, and a lot of AI agents just aren't yet able to do that kind of sort of mental simulation. The last feature that I think is really important that I'm interested in for this MARC competition, and this is actually related to AI safety, is our ability, the human ability to think in terms of goal-directedness of agents, even when there might not be anything, strictly speaking, like an agent from another kind of perspective. What I think is interesting here, right, not just our ability to use metaphors to sort of connect two different kinds of domains, like talking about frogs and predators, and then these very simple pixel objects that we have here, but I'm also applying some kind of goal-directedness, right? That there's an agent that wants to go do things, and it will do things by changing the world in a certain kind of way. It can get frustrated, or it might actually be able to achieve it. But whether, like in this case, if it has certain kinds of intentions, we can kind of predict how an agent's going to move in this space. I think this is an underutilized feature in the ARC corpus that currently exists. A lot of the examples there have to do with, symmetries and changing objects in certain kinds of ways. But I think an underutilized set of ideas is a human ability to be able to interpret or attribute intentionalities, goals, and values to different kinds of objects to explain why they might behave in certain kinds of ways. So those are the kinds of things that I'm interested in exploring in this MARC competition. And in some follow-up things, I will say how to sort of contribute to that effort. But here I wanted to just give an explanation of MARC in general.